Assalamualaikum warahmatullahi wabarakatuh. So welcome back to our class. So let us continue with models of the non-ideal transformer. Just to recap on what we have covered earlier. So we have seen how to analyze the ideal transformer. For instance, the transformer without all the impedance as well as reactance. To say that an ideal transformer is free from any leakage issue. All right. So once we come to the non-ideal transformer, so we have to take into account multiple issue such as leakage and as well as resistance and reactance. All right. So for this particular example, so a reasonably accurate model of a single phase transformer. So the various leakage reactance and ohmic losses, the resistance losses, which occur in a practical transformer is shown in the figure below. So this is what we have in actual or in real life transformer. So we do have first all the type of losses or type of leakage. All right, so we have, for example, the RP. All right, this is the ohmic losses which is taking place at the primary part of the transformer. All right, so we have the magnetizing reactance also occur at the primary part of the transformer. So we do have also the excitation branch. So we call this the excitation branch, which is representing the core losses, right? RO, as well as the magnetizing reactance. Okay. So all this we put at the primary side of the transformer. Okay. So R1, R2 is also actually referring to winding losses happens at both primary, so one stands for primary, and also two, so represent or stand for secondary. All right, so same goes to leakage reactance. This X1 is actually referring to primary part of the transformer. So 2 is referring to secondary part of transformer. So by the way, as we go on, so we will see how this R1 and R2 will be combined as well as X1 and S2 will be combined in order to simplify the circuit or to refer those impedance into one side of the transformer. Since we have two sides, primary and secondary, so we may simplify the circuit to refer the secondary side to primary or the other way around, primary to secondary. All right, and we can have a series connection of all impedance. All right, then of course we do have the induced voltage over here represented by E1, E2. Okay, the induced voltage with the turn ratio of N to 1. All right. And then, okay, S again, so this stands for secondary, S stands for secondary. Right. So I1 and I2, V1 and V2. Okay. So I hope you have no problem to understand or to analyze how this practical transformer works. And then, yes, we come to the circuit simplification. So the excitation branch, the one I highlight here, all right, this excitation branch comprising RO and SM is sometimes ignored or neglected. So in the analysis, so it has been removed over here, you can see. So it is a blank zone. So in the analysis, and all series resistance and reactance are combined and then referred either to the primary side or to the secondary side, as shown in figure below. So in this particular example, we have seen that at the secondary part over here, okay, there is no any impedance. There is no any component of resistor or coil and so on, so forth. Okay, so we have shifted everything to primary side of transformer. Okay, here and here. Okay, so S stand for secondary. S stand for secondary. So the figure below shows an approximate transformer model where the excitation branch has been ignored and all series resistance and reactance have been referred to the primary side of the transformer. Okay, so as simple as that. So on the other hand, figure below shows an approximate transformer model where all series resistance and reactance have been referred to the secondary side. So this is vice versa of what we have seen earlier. So no any here losses or no any series resistance or reactance in the primary side as we shifted everything to at the primary. So we have shifted everything to secondary. Okay, so R2 equal to RP plus RS. Okay, this is from primary part. So X2 equal to XP plus XS. Again, the XP is coming from primary part. In the same time, so no longer or no more excitation branch. Okay, the RO plus GSM. So no excitation branch for this analysis. So there is no particular advantage of using one model over the other. Which model is chosen in the analysis will depend on which or what information is provided by the problem to be solved. So there is no any particular advantage. Either you refer the transformer to secondary, for example, or to primary, for example. So it depends actually on the information provided by the problem to be solved. In your case, of course, it depends on the data, the information given in the question, or depend on the requirement of the question. Okay. If the question asks you to refer all the impedance into secondary, then you have to do as instructed. So per unit model of transformer when referred to primary side. So what will happen when we have the transformer which is referred to primary side? So consider the circuit in the figure below, which shows a single phase transformer of N to 1. So this is the turn ratio N to 1. And having an impedance Z1 referred to the primary side. So you have Z1 equal to R plus JX1. So we have the resistance plus the reactance. Okay, so we have V1 over here. So this is E1. So the induced voltage. Okay, we have the output voltage of V2. Again, we have the induced voltage at the second turn of the ratio E2, as well as incoming current and outgoing current I2. Right. So what we do next is we tend to apply Keychop Voltage Law, KVL. So to the primary circuit, which resulting in the voltage equation V1 equal to I Z1 plus E1. So this is the voltage drop across the impedance. The voltage drop across this impedance. So we have I1, okay, multiplied by Z1. Okay, so we have I1 multiplied by Z1. So we have plus E1. So this is the voltage at the primary turn coil. And then, so if we go further, we try to expand the equation. So using the voltage transformation ratio, equation, E1 equal E2 equal to N. So we have E1 over E2. This is equal to N, all right? And using the fact that E2 equal to V 2, so E2 equal to V2 since we don't have any voltage drop. Okay? Unless we have voltage drop over here, Z for example, and then we need to change the equation because this voltage drop over here will cause a different result or different output of V2. Okay. Then, but this example, not any Z, this means E2 equal to Z V2. Sorry. All right. So considering E2 equal to V2, we can write the previous equation as follows. So V1 I1 Z1 plus E2. This is actually E1. Okay. So E1. So from there, so we can we let V base1 be the base voltage on primary side, and dividing both the left hand and right hand side of the above equation by V base1, we obtain. So this is, we try to expand, or we try to make it a PU. Okay? We have V1 over V base1. All right. So we have IZ1 over V base1 as well as V base1. All right. So here, okay. So the base voltage on the primary side. So everything we refer to the base voltage on the primary side, V base1. So from the definition of per unit, we have V1 PU equal to V1 actual. Okay, this is actually V1 actual. Okay, all right. This is over V base1. Similarly, for second quantity, we have I1 PU, I1 over V, I base1. So Z1 PU at Z1 over Z base1, and V1 PU equal to I1 PU multiplied by Z1 PU. So hence, we can write, so from this, from this relationship, and this relationship, so we can actually put or substitute into this equation, right, for this relationship, and result in all these equations, right, all these equations, and then we try to simplify according to this formula. All right, so according to this formula, I1 PU, Z1 PU. All right, so we have over here I1 PU, I P base PU, and Z1 PU. All right. So from here also, we can actually derive furthermore to get this simplified formula. Okay. So if we define that N, so this is from N V base 1 over V base 2. So we can actually simplify the equation from here, okay, to this one. Okay. So finally, we can determine that V1 PU equal to I1 PU, Z1 PU plus Z2 PU. So now we come to the equivalent circuit. So this result allows us to represent the actual circuit with its per unit equivalent circuit as shown below. So this is what we have for the actual circuit, or the initial circuit of the practical transformer. So now we have proven that after certain level of derivation, so we are able to come up with more simplified circuit, right? So consisting V1 PU as the input, V2 PU the output, so as well as the incoming current I1 PU, and then the load current, the output current I2 PU, as well as the impedance, the PU impedance, right, Z1 PU. So just imagine from this quite complicated circuit over here, right? So we are finally able to come up with this much more simpler or easier circuit. So per unit model of transformer, when referred to secondary side, so we have seen earlier here what happened if we try to convert everything to primary side. So there is no much different if we try to do it the other way around. So on the other hand, the transformer impedance is referred to the secondary side as shown in the figure below. So we don't need to have a further derivation to prove it, but instead we just represent the PU, all right, instead of the actual. Okay, here is the actual circuit. So this is similar to what we have over here. All right. So the thing is, we have Z2 over here, Z2 over here, okay, and everything referred to Z2 or to this zone. Okay. So it can be shown that a similar equivalent circuit results with Z1 PU equal to Z2 PU. Here I1 PU, Z2 PU, okay, I2 PU, etc., etc. Okay, this is the equivalent PU circuit. Okay, so the proof show that the transformer PU impedance is the same. Okay, the impedance is the same regardless to which side of the transformer it is referred. In the PU equivalent circuit, the different voltage level disappear, and the transformer equivalent circuit is reduced to a single series impedance. Right? So we can have a much simpler circuit, which is a single series impedance. So per unit model of a transformer, because of the transformer, the per unit impedance of a transformer is the same whether it is referred to the primary or the secondary side. So regardless where the side is referred, so transformer manufacturer give the impedance. So this is what happened in the manufacturing side. So they represent their impedance, okay, of the transformer in percentage, okay, in percent, on the base of the nameplate rating. So this is what we have seen in the nameplate rating of the transformer. So once you look at the transformer rating, so the manufacturer will state over there, or will write over there, the impedance, okay, ZTPU, okay, which is given in percentage. Okay. So then the required per unit impedance is obtained by dividing the given percent impedance by 100, that is ZT percentage by 100 to get the per unit impedance, transformer impedance. So by expressing the impedance as a percent rather than as the actual value, so the actual value of course in ohm, so there is no necessity to state whether it is with respect to the primary or the secondary. It's fair enough to say that the manufacturer of the transformer has stated the impedance by not referring to either primary or the secondary, just having the percent in impedance, 30% over here. Okay. So we have done with the ZTPU. Now we see how it works. So primary side, the secondary side, so per unit model of transformer. So this is where the position of the ZTPU. So this is the dotted line is the equivalent circuit after we transform the actual transformer impedance into the PU. Okay. So ZTPU is the per unit impedance of transformer. So for distribution and power transformer, the value of the measured total internal impedance ZT is always indicated on the nameplate. So this is what we have covered earlier. So for example, in the nameplate is marked 3.6%. So the PU just divided by 100 and giving 0.036 for the ZTP PU. Okay. So it's very simple for the transformer impedance calculation in terms of per unit value. So work example, a single phase 3.6 kVA. So this is the value of apparent power, the compressed power. All right. So S, so 500 volt, 1.5 kV. So you can see this is notably, obviously, represent the step up transformer. All right. So it is stepping up by 3 times. Okay. So this is what you can immediately understand from the information given. So 500 volt to 1.5 kV or 1500 volt. So that means the transformer is stepping up by 3 times the voltage. The transformer has an impedance of 1.302 ohm with respect to the primary side. So with respect to the primary side, so find its per unit impedance with respect to the primary and secondary side. So we have Z1 over here. Okay, so it's J1.303, and then we have the turn ratio, which is 1 to 3 or 500 to 1,500. Okay. So first of all, again, find the base value. Okay, so you must start with the base value. What is the base value of V and S? Okay, of course, since we have two parts, so notify the first part, the primary part as 1, right? Here also 1. Okay, so we pick from the ratio of the transformer 500 volt at the primary side as the V base value. Okay, so it becomes the V base 1 500 volt and S base 1 9.6 kVA over here. Okay, this is the S value. So we pick this value as the S base 1. All right, so S base 1. So therefore, Z base 1, this is equal to Z base 1 square over S base, substitute the value, and then we can get 26.043 ohm for Z base 1. So giving ZTPU, so remember this is the actual Z, okay, T or the transformer A impedance, okay, divided by Z base 1. Okay, this is Z base 1, right? So here it is located at the primary side. Okay, so this is the subscription one. So we supposed to use Z base 1. Okay, put it here, Z base 1. Okay, and result in J 0.05 pu. Right, so this is the equivalent circuit of the ZT pu, the transformer impedance. So the primary side impedance Z1 when reflected to the secondary side becomes impedance Z2 where so this is the relationship. So n square, so this is equal to, okay, Z2 for Z2. All right. So we can relate from this relationship or from this equation in order to calculate the Z2, okay, because it is now being reflected to the secondary side. Okay, so secondary sides, so we can actually calculate from this relationship to find the value of Z2. Okay. And then again, of course, this is what I have explained before. So we have n equal to Z1 over V1 over V2. So the ratio 1 to 3. So 1 over 3 or 1 to 3. So this is the value of n over here. Okay. And then from here, so this is known. So this is provided the equation Z1. So we have J 1.302 over n square. N is 1 over 3. Okay, so we have 1 over 3 square, thus giving us Z2 equal to J 11.718 ohm. Okay, so this is how we calculate the value of Z2 when we reflect or we refer Z1 to secondary side. So now it's primary side over here. So we have secondary side over here. So with the new Z2 reflected from primary. Okay, reflected from primary to secondary. So V base 2. Alright, so we have done with the Z calculation. Now we move on with base analysis or base calculation of Z base 2 and S base 2. So way to select, so choose 1500 from this ratio. Okay, and then as base 2, of course, it is given from the beginning of the question over here. Okay, so what next? So therefore, we continue with z base 2. So we have v square over s. So substitute again the value as v base as well as the s base, giving us 234.375 ohm. Okay. So ZT, what about ZT PU? So we have again the actual Z2. Alright, so this is taken from here, Z2 down to this equation, and this is the base value we just obtained from this. Okay, so that means the ZTPU is a Z2 actual over Z base 2. Okay, so this is actual, this is base 2. So this is equal to 0, J 0.05 PU. Okay. So this is how it looks like when you draw in the equivalent PU circuit. Okay. So this work example clearly shows that the per unit impedance of the transformer has the same value. See? Same value when viewed from the primary or referred from the primary or secondary. So we have seen that this is when we refer to secondary. Okay, so we refer to secondary. So the ZPU give us value of 0.05 PU. So what happened if you look back to when we refer to primary? So this is when you see or view from primary. So primary still same value 0.05. So this is what this node is mentioning about. Okay, so has the same value when viewed from the primary or secondary. So regardless where it is being referred, primary or secondary, it still give the same value of impedance. Okay, the work example 240 volt, 400 volt. So this is again the step up from transformer, 200 volt ampere DS. Okay, so it can be it can be the N, the ratio. So transformer operated at 200 volt. So this is 230 volt, the actual supplied voltage or operated voltage. Okay, so has an internal impedance of J 4.0. This is the internal impedance J 4.0 as seen from the low voltage side. So the low voltage side means 240 volt side or primary side. So this low voltage means the primary side. Okay, and 10 ohm load on the secondary. So yes, secondary. So we put another impedance over here or resistance with 10 ohm value. So they use the per unit method to determine actual primary and secondary current. So we are instructed to find the value of I actual, I1 actual, and I2 actual. Okay. So the transformer information provided is that of the low voltage side referred equivalent circuit shown below. So this is what we refer scenes from low voltage or from primary side of the transformer. So this is where the location of ZT, okay, J 4.0. Again, start with base value or base voltage and base parent power, complex power VA. Okay, so S base 1 equal to S base 2. This is 2000 volt ampere. Okay, we simply take from the equation 2000 volt ampere. So V base 1, V base 2. This is taken from the ratio of the transformer here. All right, ratio of the transformer. So it becomes the V base. So calculate the unknown base quantity and impedance. So SI. So we have I base 1, S base 1 over V base 1. So this is the value. So I base 2, S base 2 over V base 2. So 2000 over 400. So this is for I base 2. So similarly, same process goes to Z base 1, so V square over S, so we have 28.8, so Z base 2, so we have V base 2 squared over S base 2, so 400 over 2000, we have 80 ohm, right? So now convert SI quantity into per unit quantity, therefore per unit value of source voltage is Vs, this is actual, okay, this is actual source voltage at the primary, okay. So we divide by V base 1. So this is again for primary, the source voltage. So this is from the base voltage 1. Okay, if we refer to the circuit, so this is the actual, okay, Vs, the source voltage. So this is 240, our base value at the primary side. Okay, 240. So yes, 230 over 240, 0.958 pu. So per unit value of transformer impedance referred to primary. So referred to primary, so we take ZT, which is J4 over Z base 1. We just calculate here, okay, into here. Okay, ZT, this is provided in question here. Okay, as seen from the low voltage side or as seen from the primary, or we can see from this circuit. Okay, this circuit ZT, and then we can calculate the value of ZT PU, which is 0.139 PU. So PU value of load impedance ZL over Z base 2. So load impedance means the load located at the secondary side or the right hand side of the transformer here. Okay, so the load location or the load side of the transformer. So this is the Z value, the impedance. Okay, so we have ZL, the load part, or the secondary part PUs. We have the actual, which is 10 ohms divided by Z base 2. We calculate over here. Okay, Z base 2. And then we get the ZL 0.125 pu. So draw the per unit equivalent circuit. So the per unit equivalent circuit is shown in the figure below. So this is the VS pu. We calculate. So we have 230 just now over 240. So we have I1 pu. So we have ZT pu. This is at the primary side or the low voltage side. So this is the Z, okay, the load impedance at load, of course, right? So I1 and I2 at the load, I1 at the source. Okay, so this is much simpler. So we just need to apply KVL again, the Keychop Voltage Law. So we have the V source over here. Okay, so we have voltage drop across ZT as well as voltage drop across ZL. Okay, so come up with this equation. So we have minus Vs plus IL. So again, this is the voltage drop occur at ZT, and this is voltage drop occur at load impedance. Okay, so rearrange in terms of IL. So we have Vs over Z total. This is actually Z total, ZT transformer plus ZL, Z load. Okay, so then substitute all the value. The S 0.958, and then the total Z. We might get the IL, okay, the load current PU, this is 5.125, etc. Okay. Then the actual from ILPU, so you just multiply by I base 2. Okay, why I base 2? Because it is again the load current. Load current happen at or flow at the secondary side of the transformer. So basically we take the I base 2 value. Okay, multiply by LPU, ILPU, so we can get the IL actual. Okay, this is the IL actual. So IL actual, sorry, IP actual now, the primary current. Again, just multiply by I base 1. So since the primary current flow at the primary side, so I base 1, so we have the IP multiplied by 8.33, the I base 1. And finally, the IP actual is 42.691 minus 48.03. So a simple comparison, if we have a direct calculation, so we have a straight away calculation using actual values. So we try to avoid the transformation of PU, all right, the per unit in the middle of the analysis by having the actual value. Okay, so by having the actual value, load impedance referred to the primary side is, okay, this is again the ratio, the relationship, so n square, all right, so this is actually ZL prime, meaning the new ZL. So this is ZL prime over ZL, okay. ZL is the existing ZL we have in the question, okay. In the question, the existing, all right, but so this is 10 ohm actually in the question, okay, 10 ohm. But ZL prime is the new ZL when we refer to primary. This means we try to cross over from secondary where the ZL is located, cross over to primary side of the transformer. Okay, so this is the relationship n square equal to ZL square over ZL. Okay, then we rearrange. We can get in terms of Z prime L, so the new ZL, so the n square, n is 240 over 400, the voltage ratio of the transformer, and then this is ZL, the load impedance, 10 ohms, and finally we can get the 3.6 ohm for the new ZL. Okay, so here is the existing ZT J4 at the primary. So this is the new coming ZL, from secondary. So everything have been shifted, especially ZL, to primary part of the transformer. Okay, so IP current is again, if you apply KVL, so Vs equal to ZT, IP ZT plus IP ZL. Okay, here after you rearrange the equation, you have IP equal to Zs over Zt plus Zl. Okay, Zt plus Zl. So 230 plus 3.6 plus J4. So this is 3.6, so the J4. So IP 42.739, negative 48.013 ampere. So it looks like that the value of IP, the actual IP, is more or less identical to what we have analyzed earlier. Okay, this value, right? Okay, again, thank you very much for your time. We'll see you again in the next video, and hopefully you enjoy what I have explained. Thank you very much. See you again.